Hello, so today we'll be discussing about periodic motion. So for this item, it's about describing oscillation. So if an object on a horizontal frictionless surface is attached to a spring, displaced and then released, it will oscillate. If it is displaced 0.12 meters from its equilibrium position and then released with zero initial speed, then after zero point 0.8 seconds, its displacement is found to be zero point 0.12 meters on the opposite side, and it has passed the equilibrium position once during this interval. So we will find the amplitude, the period, and the frequency. So in finding the amplitude, since the object moves a distance of 0.12 meters on either side of the equilibrium position, this means that the amplitude is also 0.12 meters since it went back. So for B, in looking for the period, so in zero point 0.8 seconds, the object completes half of a cycle. So one period is equivalent to two half of a cycle. So we will just multiply zero point 0.8 to 2, and we will be getting 1.6 seconds as our period. So for C, frequency is just equal to 1 over the period, and it's 1 over 1.6 seconds, and we will be getting 0.625 hertz. For this item, we'll be discussing about simple harmonic motion. In a physics lab, you attach a zero point 0.2 kilogram aircraft glider to the end of an ideal spring of negligible mass and started oscillating. So the elapsed time from the glider moves through the equilibrium point to the second time it moves to the point is 2.6 seconds. So find the springs force constant. So the 2.6 seconds, that's only time to complete half a cycle. So we need a period which is 2 half cycles. So we will be multiplying 2.6 seconds to 2 to complete one whole period, and that's going to be 5.2 seconds. So since we know that omega is equals to 2 pi over the period, and that the spring's force constant is equals to mass times omega squared, we can find the force constant K. So we plug in 2 pi over t to omega squared in the equation of K equals mass times omega squared. So now we will be multiplying 0.2 kilograms to 2 pi over 5.2 seconds quantity squared, and we will be getting 0.292 newtons per meter. Now, we will be discussing about energy in simple harmonic motion. A small block is attached to an ideal spring and is moving in simple harmonic motion on a horizontal frictionless surface. The amplitude of the motion is 0.165 meters. The maximum speed of the block is 3.9 meters per second. So now we will compute the maximum magnitude of the acceleration of the block. So we can find the angular frequency by using the formula of area multiplied to angular frequency equals to maximum velocity. So we will isolate the angular frequency, which is the omega. So it's going to be omega equals maximum velocity over area. So now we plug in the values. It's going to be 3.9 meters per second over 0.165 meters, and we will be getting 23.64 rad per second. So we cancel out the meter there, and we can leave the second, and we can add rad there since it's not a vector. So now we can find the maximum magnitude of acceleration by using the formula of maximum acceleration equals to area multiplied to angular frequency squared. So now we input the values there. It's going to be 0.165 meters times 23.64 rad per second squared. Now we will be getting the maximum acceleration of 92.2 meters per second squared.